Yeah. Yeah. um, so yeah, so this is the algorithms mob. We're here with Okoth and Iron Mike. And I don't know why I call you Iron Mike all of a sudden. Hope you don't mind. But yeah, we were doing like stuff with the binary search tree. And yeah, so yeah, we were going through this, and the book, the book just dove right into like a binary tree, or I'm sorry, binary search tree. It didn't differentiate between a regular, like, it didn't differentiate between a binary tree and a binary search tree. So Mike had pointed out that, there's a difference. Binary tree is kind of like an unordered tree, whereas like, you got one node, and each node in a binary tree has at most two children. But a binary search tree has the same requirement plus an additional requirement. Whereas if you go down any left side, that value is going to be smaller than the right side. So that way you can like do search algorithms, very efficient search algorithms with a binary search tree. And like the algorithm, like here, this is the search algorithm for a binary search tree. Doesn't seem like a whole lot of code because it's a recursive code. So, and we can, but yeah, this is like, I think it's log n is the big O for this code. So very fast. And as the size increases, you don't see a dramatic increase in time. It's relatively fast as n increases. And then we wrote a method to insert a new node. We wrote a method to delete a node, and the deletion is the trickiest part. Oh yeah, here we go. So yeah, last week Mike was supposed to explain the deletion algorithm. Because it is the most complex part. It is a little bit tricky. So yeah, we were going to go over that again. So let's do that. How would you like to do this, Mike? Or Okoth, either one. I can open up the book. We can go through it again in the book.
Yeah, maybe without maybe Okoth can say if maybe he's familiar with the deletion in a binary search tree and stuff.
Maybe.
Okay. I'm not that conversant with that. And,
well, let's go over it real quick with what the book has. Hopefully that will help us. So perhaps I'll just, here we go, binary trees. So yeah, it talks about binary trees, and then we well, maybe it did. Okay, maybe it didn't differentiate between a binary tree and a binary search tree. So anyways, yeah, so here where you got J right here, this is basically a binary tree, right? Each node has at most two other nodes, a left child and a right child. Here's another one. Now on this one here, this would be considered a binary search tree because here we got our value 50. If we go down the left side, all these values are less than 50. All these values here on the right side are greater than 50. So if we're looking for a number, we know exactly which side to go down, and that cuts the number of nodes we need to look at in half right there, just by comparing one value. It cuts the number of nodes in half. And then if we take a look at 25, if we look at the left side, all the values less than 25 are on the left, all the values greater than 25 are right. So then after two comparisons, we've cut the number of nodes we need to look at. So here we only got 3 nodes left compared to 3, 6, 9, 12. So 3 out of 12, that's 1/4. After two comparisons, we've narrowed our search down to 25% remaining. So you can see the efficiency with that. So yeah, so here we build our node. We got and then so here's the search. We implemented the search. So perhaps I'll just go over this real quick since it's been a while and Okoth is joining us for the first time in a while. So yeah, the search method. So inspect the value at the node. Okay, so if we hop in, let's say anyways, we inspect the value at the node. If we found the value we're looking for, great. That would be our base case. Great, just return that and you're done. Otherwise, if the value is less, then search for it in the left subtree. If the value is greater, then search for it in the right subtree. And that's it. That's all. That's the algorithm. So to implement that, we first think about what our base case is. So if node is none, that just basically means we've exhausted our search. There's no place else to search, so we just return we didn't find it. Or if that node value equals what we're looking for, then just return it. So that's our base case, those two scenarios there. Otherwise, if it doesn't meet the base case, then we decide, do we want to look down the left child, or do we want to look down the right child? If it's less than, if the value we're looking for is less than the current value, then we go down the left child and we just say, okay, just go back up here and start over, check our base case again, and then decide which path to go down. And that's it. That's it for the recursive algorithm. And then the same for the right side. You know, if it's greater, then go down the right side. So here, if we're say like we're searching for values 61, you know, we start here at the root. 61 is bigger than 50. So here, then we just go down the right child. So now we pass in this node to our search method, right? And so now we're just dealing with that part, and we forgot about all that. 61 is less than 75. So then we can narrow it down again. Now we're just dealing with that. 61 is greater than 56. So we pass in this. And then when this comes to our base case, it's going to say, hey, we've reached our base case, and return this node as the answer. So that's the search method. And yeah, we implemented it right there. So now, then insertion. So the first thing we need to do when we insert is figure out where we need to, you got to find a spot to insert it at. So So basically, yeah, if we're inserting 45, 45 is less than 50, so we go down the left side. It's greater than 25, go down the right. It's greater than 33, go down the right. It's greater than 40, go down the right. And then boom, we've reached our, there's no place to go after 40, so we can just attach it as the right child since 45 is greater than 40. And that's insert in a nutshell. Yeah, for a binary search tree, that's insert in a nutshell. You can get a little bit more complicated insert algorithms when you're dealing with, I think they're called AVT, I forget.
AV search tree.
AV search tree. Yeah, so with an AV search tree, that will automatically rebalance the tree. And I think we were
Rotation.
talking, yeah, with the rotation. I think we were talking a little bit about that.
Yeah.
So because with just
it's called AVL trees, I think.
Yeah, that's it. AVL tree.
Yeah.
Because if we just do like plain old insertions, I can't find a picture on here. We could get a binary search tree that basically looks like a linked list. And in that case, even though we have a binary search tree, since it hasn't been balanced, we can get a runtime close to, or it would be a linear runtime, right? So binary search trees, depending like this is a good binary search tree. It's very well balanced. But if it looks like a linked list, if it's unbalanced, or it looks like a linked list, your best case scenario would be log n, but then it does have a worst case runtime, which would be n. So, oh yeah, here's the example I was looking for. So yeah, say like we insert the number 1, then we insert the number 2, then we insert the number 3, then we insert the number 4 and number 5. Then we end up with a binary search tree that essentially is a linked list, and we're not getting any benefit out of that. So the key is when you create a binary search tree, when you insert the values, you don't want your values already sorted, because if you insert a sorted list into a binary search tree, you're going to end up with a linked list. So when you're creating a binary search tree, it's best to have like randomized values and create your tree with a randomized list of values. And then you'll probably most likely when you get random data and you create a BST tree with your random data, you usually, and this is true, there's been like studies done on it, you'll usually wind up with a well-balanced tree. Not all the time, but usually. All right, so that covers insertion. I guess we did not look at the code, but it's basically the same as the search code. Just need to find where you need to insert it at. So our base case is kind of nested. So here's our base case right there. It's nested within the if and elif. So if value is less than, then you're going to check the left child. If no.leftChild is none, then we can insert it. Else, so that would be the base case. Else we recursively call insert again. And then same thing for the right side, just in doing the same thing for the right side.
Yes.
Oh, hey, Mikhail is here. Awesome.
Hello?
Hello, how's it going?
Not so bad on you.
Doing pretty good.
Hi, Mikael.
Hello, Mikhail.
Hi.
Man, trying to make this window bigger now. It won't go big. Oh, there we go. Okay.
I had that bug as well.
Okay.
That's a bug.
Yeah, I had to click somewhere else and then click on it. It seemed like. Whew.
Is this the biggest we get?
Yeah, this is the most people I've had in a long time. It's good to see you all.
I mean, is this the biggest screen we can get?
Is this a what? Okay. So, oh, is this the biggest screen we can get? Is that what you were asking?
So Okoth, if you right click on your screen and do show controls on your video, and do show controls, you'll be able to go full screen with your video.
Oh, okay. That's cool. I'll have to try that next time.
Yeah,
Show
but I think
control.
it's
It's
only
show control.
yeah, it's only for the guys who are watching. For
Does it work on us?
for the host,
Right.
for the host, I think it doesn't work for you.
Right. That makes sense. That's pretty cool. I'm glad you mentioned that.
So
Yeah.
I'm showing control.
When you hover on your screen, you'll see there. You are able to expand that.
All right. So,
Good.
so now we move on to deletion. So yeah, so deletion is the least straightforward operation within a binary tree. So yeah, let's say we want to delete the 4 from this binary tree. We have to find out where it is. So we search down, we find 4. And since it's at a leaf node, like all these at the bottom here, they're considered leaf nodes because they don't have any children, right? So they're all considered leaf nodes. Like you can think of this as like a tree, right? These are all branches. They all branch somewhere else. And finally we get to the leaves of the tree and they don't have anything. Nothing grows from the leaf. So we can just cut it out. We can just tear the leaf off without having any impact. So, but if we want to delete number 10, and that's kind of a problem because here we got a leaf attached to it. So if we get rid of number 10, we also get rid of the leaf, but we need to preserve that leaf. So when we cut out 10, we have to do something with that 11. We have to put it back in. We have to route it some way so we don't lose it. We don't drop it off the tree. We want to keep it on there. So when a node only has Okay, thanks, Okoth. So when a node Okay, I muted Okoth. I think I don't know. Anyway, so when a node only has one child, if it's the right child, we can just take that 11 and attach it to where it was. So if the node being deleted has no children, simply delete it. If the node being deleted has one child, delete it and plug the child into the spot where the deleted node was. So I guess it doesn't matter if it was it wouldn't matter if it's the right child or the left child. Just plug it in to where it was. So 0 children, simply delete it. 1 child, take that 1 child, plug it into where the deleted node was. Now we get into the case where there's 2 children, right? If we want to delete 56 there. Then when deleting a node with 2 children, we want to replace the deleted node with the successor node. And the successor node is a child node whose value is the least of all values that are greater than the deleted node. So, for example, like here, so 56, we're looking for a child of 56 that has the next so whose value is the least of all values that are greater than the deleted node. So basically, if there was a 57, 57 would be the successor node because it's greater than the node that we want to delete, and it would be the smallest of all the values that it could possibly be. 52 would not qualify because it's less than 56. But here we see 61. 61 would be the successor node. And there is an algorithm to find the successor node. So let's, and it goes through that here. So here we would take 61, plug it into 56, and then here's our new tree. We got 61 with the left child 52. So yeah, so how does the computer find the successor value? There's an algorithm for that. So the algorithm is visit the right child of the deleted node, and then keep on visiting the left child of each subsequent child until there is no more left child. So basically, so the successor, if we look at this tree here, the successor value for 50 would be 52 right here. And that's because it's, if we just look at the right side of the tree, we want to look at the right side of the tree and grab the smallest value in that. That's going to guarantee that it's greater than 50, that it's the next value, that is the value that's the next value greater than 50. So if there was a 51, 51 would be the successor. But there's no 51, so 52 qualifies. And we can easily find that with an algorithm by visiting the right child, which would be 75, and then keep going down and keep visiting the left child. So we'd visit left child 61, left child 52. There's no more left childs to visit, so we're done. And we stopped on 52, so that would be our successor. So yeah, so right there, yeah, if we're looking for the successor value of 50, there's a successor value, so we're going to plug that up into 52 now, and then that would be the new tree, and we're done. So those are special cases. You know, when there's 0 children, simply delete it. If there's 1 child, then take that child and plug it into its place. If there's 2 child, then you need to find the successor value and move the successor value up into the place. And then, however, there's one, okay, so it looks like there's still one more case. That's where the successor node has a right child of its own. Okay, so yeah, so one more case. So yeah, when the successor node has a right child of its own, so yeah, so in this case, so we want to delete 50. We find the successor value, it's 52, but it has a right child 55. So in this case, we can't simply plug the successor node 52 into the root, since we'd leave, you know, this hanging. So then what do we do with it? If the successor node has a right child, after plugging the successor into the spot of the deleted node, take the right child of the successor node and turn it into the left child of the parent of the successor node. So it's basically like, so like we're deleting 50, we find the successor. We basically treat this as if we're deleting 52 from the tree. So what do we do when we delete a node that only has one child? We take this and just plug it up there. So this is going to, so 55 is going to go where 52 is. 52 is going to go where 50 is. And we're done. So that's it. So we got, so for deletion, there are 4 special circumstances that we have to consider. And they can all be done recursively. And that's a lot of comments. Yeah, that's the deletion. Looks like they got a helper method here called lift too. But yeah. So I'm not sure. I'm not sure if we actually implemented delete last time we met, or if we were, or maybe we did and we were going to do it again.
Yeah, we started implementing delete, but I think where we got confused was the area where we have the right successor we have a right child for the successor.
Okay.
So also there's something we did that was sort of, we were saying it was incorrect. You can see in the comments.
Oh, right. Incorrect. Dot right child. Then the correct one would be that successor dot parent dot left child is equal to successor dot right child. Yeah.
Yeah, and we were trying to figure out how to get the parent.
Right. So there's a,
and something has just popped out in my mind. It's like we could just assign the value of the right child to the successor, or that will not be a node in itself.
yeah, I mean, yeah, we could do that. Yeah. So there's a lot of different ways. Yeah, exactly. I mean, yeah, we could do that way. Depends what kind of objects we're dealing with. If we're just dealing with integers as values, and that's the only value we hold in our nodes, and yeah, it'd probably be simple just to update that value and change it. But yeah, there's a lot of different ways to get the parent, a lot of different ways to update the values or the nodes. So you can create ways that are very specific to your need, or you can create, you could create a tree that's very specific to your need, or you can create a tree that's a little bit more generic and can handle a lot of different use cases. So it depends what you want to do, right? Or what your needs are. You got to think about memory. You got to think about speed. So it all depends on, your specific use case. A few different options would be like, to get the parent, we could actually store that value in the node, whereas every node knows who is their parent. You can just ask the node, who's your parent? And the node would tell you. Of course, then you have to update that whenever you move that node around, right? So like, yeah, so here we are importing node. Where's node at? I think it's right here. So yeah, here a node has a left child, it has a right child. We could say, well, now it has a parent, right? Every node knows its parent. But that's one more thing to track. So every time we move the node, we'd have to make sure that gets updated correctly. That might increase speed of finding out who the parent is, depending on how else. I'm not 100% sure, but it definitely increases memory, right? The node now is getting increased in memory. So if you're strapped for memory, like if you're developing this for a very small device that doesn't have a lot of memory, then you might not want to go that way. I think in the future, most people won't care about memory, but it's still a good thing to think about. Yeah, so you can assign a parent attribute to node and just keep track of that. As you're doing your search, you can keep track of like when we're doing the deletion, we can always keep track of the last visited node, which would be the parent node of any node we're currently looking at.
Mm-hmm.
The exception to that would be the root. The root would not have a parent, right? So,
what if you just do maybe successor equals successor.next? Does that override? Like, is that done by reference, or if you just, because you want the right child of the successor to be the successor, to be at the point where the successor is.
right.
So if your successor equals successor.right child.
So you got a successor equals successor dot right child. So like overwrite successor with its.
Yeah.
So the one problem with this is, let me see. So you got to think of it as links, right? Because right now we've got a parent, and the parent is pointing to the successor, and it's also pointing to a right child, right? So I'll put it over here. So the successor has two links. The left child of the parent is a successor. The right child of the parent is the right child. So what we want to do, and then the successor also has a right child. So we basically want to move the right child here, right? So we could copy it over like this. We could just say successor equals successor right child, except this link here, we didn't change it because it's on the parent. So we actually need to change the parent's left child, because the parent left child is pointing to the successor in memory space. So this is a memory address. So that memory address is pointing to the successor. So we want to, so I guess maybe this overwrites that memory address, but it might not work like that with, in all languages, right? You might not get the same results in all languages.
Yeah.
So the best practice, or the way that it's taught, is you take that parent and you just replace the memory address and point it to the right child. So now you're just going to basically end up like that. So at least that's, I don't know, that's the way I was taught, right? You're going to change the parents. You're going to change the parents, whatever address it's pointing to. You want to point it to the right child address. Yeah.
Yeah,
I don't
that
know.
makes sense.
We could try it this way and see what happens, but I'm
Yeah,
not
I have my doubts about this.
because what this is actually, because I don't think this will work, because what happens is we're redefining a new variable. This is a variable assignment. And what happens when we do a variable assignment in a language is going to first allocate memory for that variable. So it's going to grab new memory space, right? And then it's going to take that, whatever we're assigning, it's going to take that value and put it into new memory space. So yeah, I don't think that will work because this is basically a variable assignment. Even though it seems like we're overriding that memory space, we don't overwrite memory space when we do that. It actually allocates new memory space and assigns it there. If we do, say, successor, then it's going to end up with our right child data, but the parent is going to be pointing to our older successor value still. So we want to actually change what the parent is pointing to. All right. So what are we? Yeah. Let's. I'm going to set up the link to the VS Code session, and then let's start writing this.
Nice.
Here we go. Hey, Mikal, you need to be added back in, or do you want to stay dropped out? I'll just add you in. You can drop out if you need to, I guess. I know sometimes I couldn't figure out the other day how to get rid of the muted sign. Like,
I think when you go full screen, it goes away. Like what I just told you.
Okay. Yeah, because when I was trying to watch the other day, it was that muted sign. I would drop out of the session because the muted sign was in my way. So that's cool. I didn't know I could go full screen. I'll have to try that next time in that situation.
Mm-hmm. Oh, you've shared the code, the link. Okay, thanks.
You're welcome.
Oh. Mm-hmm. I am in. And Mikhail is in. Nice.
Yeah. Let's see. So I don't know if you want me to talk about what our current implementation is. I haven't really looked at it yet. Or someone feel free to take a look at the code, and if you see something that needs to make changes, go ahead and explain to us what you're doing while you're making the change.
So we are currently deleting.
Yeah, we're implementing the delete method. So
Um, so if we are first checking if actually this is still our base. This is still our base scenario. We are not recursing yet.
yeah, not yet. We don't have any recursive call. I think this would be our base case. We found the value we want to delete, and so we're checking out. So then we check which circumstance it is. If it's a leaf child, then we just, this is a little bit incorrect, I think. Not necessarily incorrect, a little bit incorrect. Actually it is incorrect. Maybe it is, I don't know. Well, so this is what I'm thinking.
Yeah.
So here where we're assigning root is equal to none, we're not changing, like what I was just explaining, we're not changing what the parent address is. Like parent dot, so here we got, I don't know, this is either, so yeah, so the root here has a parent, right?
Yeah.
And the parent, I don't know, this could be the right child or left child, but that is still an address in the parent's memory. Like parent.rightChild points to a memory space address, and now what we're saying is that memory space address that points to root, we're putting none in there. So when we call parent.leftChild, yeah, it's going to return none, but it's still going out to a memory space, and that memory space is saying, hey, there's something in here. It is none.
Hello.
There's something in here.
Yeah, I think you broke for me a little bit. You're saying parent.left child is going to return none?
Yeah, so whatever this root is, if it's a left child or right child, the parent still has an address, right? Memory space still has an address pointing to a memory space, even though inside that memory space is none. The more correct way would be to take root.parent and then, yeah, I don't know, it's probably fine because, like, again, we need to know whether or not it's left child or right child.
Yeah.
But yeah,
go ahead.
Yeah, go ahead. Because yeah, I mean, if we knew.
Go ahead.
I mean, if we knew if root was the left child or right child of the parent, then we could say root.parent, we'll just say left child is equal to none. And then that way, and then that would be it. But our implementation doesn't allow us to do that, I think.
Yeah, I think the reason I see this is correct is that if root had any other children, for example, if there were subtrees on root and you've already set root to none, those other subtrees, I think they will be hanging or something, and the garbage collector will collect them. Am I correct?
So in this case, yeah, so there are no subtrees. And when we put root to none, the garbage collector is not going to collect root. It'll still be taking up memory space. That's why it's essentially not correct. I mean, it is you'll get I think we'll get the same behavior that we want, but we're still taking up memory space when we delete this value. Because we don't actually we don't actually cut off that memory space from the tree.
But if root has a parent, you can't get the child of root from the parent now. You can't get parent.none.next.
Right. We can't get that with I don't think we can get that with our current implementation. We'd have to change it. Yeah. Let's see.
I don't know if Mikhail or Okoth have something to say.
Okay. That's today. All right. Hold on, I'll be right back. I gotta do something. Sorry. Okay, I'm back.
Okay. Yeah, I was just reading through this. So
Okay.
I was saying, I think where we got stuck, okay, I think maybe I moved further from this discussion. So maybe we can just finish up with that first.
Oh.
Yeah.
Yeah, I think it's
Like, yeah, I was thinking, what's the best way to make the garbage collector collect something?
cut it
Is
off.
it by
Cut the link, right? So here the parent is still pointing to this value. This is still, none is still a value, and it takes up memory space. So the parent is still pointing to that value in memory space. So the only way to have the garbage collector pick up that memory space is to take that, to go to the parent and say, hey, parent, you have no more child. Your parent, your whatever it is,
but
parent right child is not.
But when we search, if we look at our search algorithm, we only check if right child or if left child is none.
Right. Yeah, I don't think, like I said, I don't think we can do that with our current implementation.
Yeah. Okay. Yeah.
That might be something. I think that might be something to look at if we want to go down that path in the future. That would be something to look at and improve upon. So, I mean, I was just, I think this is fine for now. But it's just something, to be aware of, like, because looking at the implementation they have in the book, let's see. I'm trying to figure out their implementation in the book.
So I can just come here.
Seems like they got a delete method that they're using. Yeah, I'm not. Oh, that's the recursive. Yeah. Okay. So if the current node is. Yeah. Okay. Yeah, the book actually implements it the way I was telling you. So there is a way we can.
Oh, with a parent.
Yeah, it does assign the parent as none. Or not the parent as none, but it assigns the parent, whether it's the left child or right child, as none. And it does that in a very pretty cool way.
Okay.
So
Yeah, maybe we can go through that.
I don't know if you want to look through it now, or
I don't know.
it's up to you. I mean, we can keep going. We can keep doing what we're doing.
Yeah.
But yeah, so
Okay.
it looks like there is a way to keep track of the parents, I guess. It doesn't actually keep track of it. But, well, yeah, with the recursive, it's I don't know, recursive algorithms.
Oh, okay.
Yeah, it does it with like with part of the recursive algorithm. So
I don't know if I'm going down a rabbit hole right here.
okay. I don't know either. What are we doing?
Yeah, so
You want to tell us what we're doing?
I was just thinking like maybe we will need an extra variable to track the assignments. I think we were just assigning successor equals value equals successor.value. So I was just thinking maybe we need to create a new root, and then now we can, after all is done, we can assign root to be the new root because we've assigned its children to the current roots. And then maybe we'll have this successor, and we still have the successor, and we can say successor dot value equals successor dot right child. Oh, but this is a case where both of the children are like where the root has both children. Yeah, Mikhail, you want to say something?
Yeah, I think you just have to when you move the successor, you have to replace it by known. I think it's the only. So you create a new root. I think it's right. New root equals successor. New root dot right child, and it's right. New root dot left child 2. And then you've got to here child.
Yeah.
Yes, and then you've got to. I don't know how to do it, but you've got to do something so that the parent of the successor left child is known because you move the successor from the bottom to no.
Yeah, I think this is correct. I just wanted to comment on this. How do I do that? Yeah, here. So because we moved the successor from, yeah. So I think what I was thinking was just assigning the value of the successor to the value of the right child. And then I assign successor dot left child to be successor. Yeah, go ahead.
Successor is not it's a function. So you've got new root equals successor of root.
Yeah, I think we.
First line, new root equal.
Oh, sorry. Yeah.
So users.
So I want to before I assign a new root, I want to have this stored somewhere so that I don't mess with it. I just want this one here, and then we can have this instead of just calling, or maybe we can call that function, but so we can have it as such. And then now, since I know this successor, I can change its right child to be the child of the successor's right child, and its left child to be the child of the successor's left child.
But
And
the
then those are the ones that I make. Yeah.
You need some backtracking because when you get the left child in the successor function, you want to put a known in the parent of the child, but I don't know how you can you don't have any way to get back to the parent currently.
Yeah.
No, we don't.
Yeah.
And the problem is in this is to get back to the parent.
Yeah.
So
you've got to do
I'm
some
trying
kind
to
of backtracking and to keep
Yeah.
the value of the parent.
Yeah, let's
Okay,
take a look at the book's implementation. Yeah, we're running out of. Yeah, exactly what Mikhail said. We need, some backtracking, which can be done with the recursive algorithm because when it unwinds, it backtracks. So let's take a look at the delete method, and then after we go through this, we'll wrap it up for the day, and then we'll see if we'll have better luck next week. Let's see, can you see this all right? Let me try to make this bigger. All right, so we take a look at is that too big or is it good?
It's good.
Okay. So yeah, so our delete. So we get passed in the value to delete, and we get passed in a node. Basically, we pass in the root of the tree to begin with. So the base case is when we've hit the bottom of the tree and the parent node has no children. So yeah, basically, yeah, if node is none, then we just return none, right? Yeah, we can't find, basically, if we can't find the value to delete, then we just return none. Otherwise, if the value we're deleting is less or greater than the current node, then we set the left or right child respectively to be the return value of the recursive call of this very method on the current node's left or right subtree. So let's take a look at the code. So the value that we want to delete is less than the node's value. And what we're going to do is we're going to take the node.leftChild and we're assigning it, and then we're recursively calling delete on the value to delete, and then we're passing in node.leftChild. So yeah, so we take node.leftChild and we assign it to whatever returns from the recursive call here. So we return the current node and its subtree if existent to be used as the new value of its parent's left or right child. And then, yeah, and then return node. So, and then else if value to delete is greater than node.value, we want node.rightChild, basically the same thing we did with the left child, and then we return node. If the current node is the one we want to delete, then, and so here's where we get our special circumstances. The current node has no left child. We delete it by returning its right child. So node.leftChild is none, then we just return node.rightChild. Otherwise, if node.rightChild is none, then we return node.leftChild. And this takes care of actually 3 special circumstances here. So if node.leftChild is none and node.rightChild is none, then this actually just returns none, right?
Yeah.
So it takes care of the 3 special cases where there's one or 2 special cases. Well, anyways, where there's one child and where there's no childs. Otherwise, if the current node has 2 children, then we delete the current node by calling the lift function, which changes the current node's value to the value of the successor node. So node.rightChild is equal to successor. We got it called successor in our implementation. Successor node.rightChild node, then we return node. And here's the lift. Here's the lift method. Basically, yeah, goes down the left child, and then returns the node. We return the successor's right child. If the node to delete .value equals node.value, return the successor's node's right child to be now used as the parent's left child. I don't know. I'm a little bit confused about all this. I'll have to like dive into it. But that's how
this actually it doesn't show like where you're assigning the right child for the root that you've just added, or it's just deleting and returning nuns. I'm not sure if that's correct.
It is assigning, like when the recursive call is done, it unwinds, and I think it is taking that parent.leftChild and assigning it, because here this would be the parent.leftChild, and we're saying assign it to the return of that. Or if it's parent.rightChild, assign it to the. So it's doing it
Yeah. Okay.
right here because we recursively call it there, and then when it returns, we're assigning it to parent.right child. Or if it was a left child, then we're assigning it to parent.left child. So it's a little bit, it's a bit complicated. What, right? There's probably a better way to implement it because I don't remember having to go through this much trouble when I implemented it many years ago. Or 1 year ago, 2 years ago. But what I'm going to do is I'm going to paste this code into the algorithms, into the chat channel on algorithms. That way you can check it out. Hopefully it doesn't look like, I'm not sure if this is going to be formatted correctly. Yeah, the format looks off. Let me try to redo that. But I'm going to paste this. So I don't know if you have this book, right?
Yeah, I think I can get the book.
Yeah. Okay, hold on. Let me. I'm going to paste this in, and then hold on. Okay, this needs to be indented twice. I'm just fixing the format on it. And then oops. Wait, LF value to delete equals that, do that, comment. Oh, there's the return. Okay. Turn node. Oy, oy, oy. LF value to delete is greater than node.value. Then node.right child equals that, return node. And then that, LF that, space. Whew. Okay, halfway done, I think.
You're like literally formatting it?
Yeah. And I'll paste it into the Slack. I'll paste it in the Slack so you can look over it if you want to throughout the week and try to understand it more. Because I don't know. Because for me, I'd have to really look at it and dive into it to understand this, I think. Let's see. I mean, it makes sense. Like, it makes sense if I don't think about it too much. But once I start thinking about it a lot, it doesn't make sense anymore. I think that's normal when you're dealing with recursive algorithms. But anyway, so return that, this node, and then LF node dot right child, and we're gonna return node dot left child, and then All right, and then comment.
Well,
All right, I think I'm done formatting it. I'll paste this in Slack, and then it'll be there for you if you wanted to look
okay.
at it more. And then we'll try to, and then next week we'll work on implementing the delete method. Yeah, we'll try to finish it up next week, the delete method. I think,
Yeah.
I guess I think I kind of started off. I mean, I did start us off down this path. And I think this is correct. Like, we could probably still use this code, but we need to, instead of like root equals none, we need to like do return values and put something above here, right? So like, yeah, I mean, yeah, do return values, but then put our recursive calls up here. And then this would be part of the, and then this would be, and then when those recursive calls unwinds, then we would get that whatever that return value is that we returned here would get assigned appropriately. But thinking, yeah, I'll see if, hopefully I have time during the week to dive into this a little bit more, and then maybe I can hopefully clarify any confusions there are.
Yeah. It's confusing as they promised.
Yeah, it's not as straightforward. And then when you throw in recursive calls, it kind of makes it a little bit more tricky to think about. It's not as straightforward as the other recursive calls we were coming across. But so we'll do that next week, and then just that'll be it for today.
Okay.
Cool.
Okay.
Hey, thanks, Mikal. Thanks, Mike, and for joining, and thanks, Okoth. Sorry you had to leave early, but yeah, the video is recorded, so you can watch it later.
Thank you.
Cool. Thank you.
Bye.
Bye-bye.
Yeah. Bye.
See ya.
See ya.